Every successful cloud architecture rests on a foundation of rigorous mathematical routing. Novice engineers often look at Google Cloud Platform as a buffet menu, picking services based on familiarity. Experts treat it as a strict routing matrix, where every workload has exactly one correct destination. The consequences of guessing are immediate. Misclassifying data or over-provisioning compute resources leads directly to exponential cost increases and measurable latency spikes. To prevent this, we must build an objective decision matrix. This matrix maps application workloads and data lifecycles to precise Google Cloud Platform services based entirely on their technical constraints. We will construct this logic across three specific areas: selecting serverless compute, configuring event-driven triggers, and mapping storage tiers. Mastering this routing logic ensures an application transitions from a functional state to a financially viable, scalable architecture. The first branch of our decision matrix defines the baseline for compute workloads. For broad, stateless, containerized applications that need to handle web traffic, Cloud Run serves as the primary vehicle. It scales HTTP requests effectively and supports any language. This compute routing matrix shows the divergence. On the left, we have standard containerized applications. On the right, we have a very specific execution profile, event-driven processing. Workloads that are purely event-based, scale strictly by event count, and execute rapidly require routing to Cloud Run functions rather than standard web containers. This details the exact sequence for Cloud Run functions. Notice the workflow diagram. A calendar event points to the function, then to a storage icon. The final bullet point specifies these functions are stateless, requiring data to be persisted to be shared outside. This architectural constraint is absolute. Because functions spin up to react to a trigger and then immediately spin down, any data generated during that execution will be lost unless it is intentionally written to external storage. This routing logic translates directly to how you execute deployments in the command line interface. Consider a practical scenario where you need to analyze a new file immediately after it is uploaded to a bucket. Diagnostic Question 05 presents this scenario. A Python script analyzes files added to a bucket. Option A provides the precise syntax. Configure the trigger, event parameter as google.storage.object.finalize. This executes the function the moment the file write completes. Selecting the compute environment is dictated entirely by whether the workload is a persistent system or a transient reaction to a specific trigger event. Once compute is routed, the focus shifts to data lifecycles. The primary sorting mechanism for data routing is classifying the asset as either structured or unstructured. Structured data is automatically routed to dedicated database services. Unstructured data, however, requires a lifecycle evaluation based entirely on access frequency. This flowchart maps the precise evaluation logic for unstructured storage classes. Moving right from the start, the first node asks if the data is read less than once per year. Answering yes routes downward to archive storage. Archive storage offers the lowest storage costs but the highest retrieval costs, making it viable exclusively for data accessed less than once every 365 days. If the answer is no, the logic moves to the next node. Is it read less than once per 90 days? A yes routes down to cold line storage. Cold line storage is engineered for quarterly access patterns, making it the correct routing destination for disaster recovery backups and legacy data. Moving right again, we test for a 30-day window. A yes here points to nearline storage. Nearline storage is the optimal tier for monthly access requirements, such as end-of-month reporting data or recent analytical datasets. Finally, follow the red No branch pointing downward at the far right. Only data that fails all three low-frequency tests, meaning it is accessed frequently, should be placed in standard storage. Ignoring these exact 30, 90, and 365-day time horizons forces organizations to pay premium hot storage rates for cold data, actively undermining the financial viability of the cloud environment. Once the service tier is selected, the final routing layer is geographic location and availability configuration. Consider a scenario where an engineer must create a bucket serving U.S. users in New York and San Francisco, while strictly excluding users in London. The goal is to provide access across a broad geographic area without implementing granular access control lists, or ACLs. Diagnostic Question 06 tests the specific CLI command needed to execute this geographic storage requirement. Option C provides the correct deployment method, running the gcloud storage buckets create command, but intentionally omitting the -- location flag. The operational logic relies on defaults. Omitting the location flag creates a multi-region bucket in the US by default. Engineers must deeply understand these default behaviors, as the system will apply its own routing logic when flags are left out. This unstructured bucket creation contrasts sharply with the requirements for structured database services. For databases like Cloud SQL, high availability requires explicit configuration. You must define automated failover using flags like -- availability type. Geographical deployment requires precise CLI flag management to balance availability, consumer latency, and bandwidth costs. This consolidated matrix is the blueprint for Google Cloud deployments. The absolute rule for compute is matching execution environments to statefulness and trigger type. Use Cloud Run functions for rapid, event-driven, stateless tasks. On the storage side, strictly map unstructured data to its access horizon. Ensure data passes the required time thresholds before deployment. Standard storage is reserved for hot, frequently accessed data only. Successful architectures rely on these exact constraints. Cloud engineers enforce rigid routing discipline, guaranteeing every workload runs on the correct service at the lowest cost.